Welcome to Lesson 13, Validation Design Stage. In this lesson, we're going to be looking at what happens in the design phase of a validation project. We're going to be taking a look at a URS, FAT, your factory acceptance test, a clean room case study, and a mixer case study. So this is the V model that's often used to describe validation activities. And you can see in the V model, we've got the user requirement, so the I, the what needs to happen, what does it need to do? The functional design, so how in concept does this work? The detailed design, how are you going to make it? What's it going to be made from? The implementation of it. Then it's installed, and that goes your IQ test is checked off your detailed design plan. Your operation of it is going to be checked as part of your OQ, and that's checked from your functional design, and your performance qualification then is tested from, well, what did you want it to do in the first place? What did it need to be able to perform? So you've got your design development on this side, and you've got your implementation phase over on this side, and that is your V model of your validation. This part of the design phase, we're going to be looking at this side of the V. So the what, the how in concept, and the detail part of it. So the design qualification considerations. What needs to be done? What do the end users need it to be able to do? So the team members would be typically including validation department, your engineering department. You would definitely have someone from quality and production in it, and you would have someone probably from QC and from maintenance, depending on what the project was. Documented verification of the proposed design is suitable for the intended purpose, so you need to have your documents all up to date and well thought out and well designed. Next thing you're going to be doing is generating your URS, your user requirement spec. So this is detailing what the end users need the item to be able to do. You're going to be generating your functional design specification, your FDS. So again, that's going to be linked up with your URS. You have to identify what are the critical components, because these are going to be the cornerstones of your validation plan, and identify what are the critical to quality characteristics, again, so that you can design a good quality validation plan around it. So the user requirement specification, the URS, this describes what the end user wants from the system. It's normally written by the end user. It needs to have a lot of detail in it, as you can imagine. It needs to be very specific. The reviews need to make sure that all the requirements are included. If you leave something out at this critical juncture, you might get a piece of equipment that doesn't do what it needs to be able to do. The document must be approved before moving on to the next stage. Any items that are needed from a health and safety or from a regulatory inspective must be included. They'd be really important. So the URS, the user requirement specification, outlines what the system must do. So what does it do? The system description and the requirements around that. The URS documentation template might look something like this. You might have your purpose and scope. You might have definitions and acronyms, your references. You might have your purpose of your system, the benefits, characteristics, assumptions, constraints, and then details about what you needed to be able to do, what you needed to interface with, what physical requirements you need from it, what technical requirements you need from it, what performance requirements you need from it. The system criticality level then would be assessed. You might have revision history if you've had a number of revisions of the document to make, and you will have to have it approved. The functional design specification, or the FDS. This describes what a system must do to meet the URS. So it gives the size of the vessels, the materials of the construction. Obviously, they have to be non-additive. Sequence of operations, so which forms the basis of an automation script so that the URS can be met. Again, it has to be very detailed. It's written by the design team in consultation with the end users because it's quite a technical document. It must be reviewed and approved. The FDS outlines how the system works and outlines the operational sequence of events. The FDS document then might have your purpose, your scope, your definitions and acronyms. You might have references in here. You have the description of your system, the user characteristics, operation support, developer guidelines, assumptions and constraints, and then you have data, functionality requirements. What's your user face requirement going to be? How's your system? Is it going to be interacting with other systems? Is there compliance issues to be considered? What records will you need? What technical requirements they are and how you need it to perform. The system criticality level is outlined, and your revision history and approvals again. So if you take a mobile phone, the user requirement specification would be really important. What does the end user want? So if it's a phone for a 15-year-old who wants to do a lot of gaming, watch a lot of YouTube, do a lot of videos on it, it needs to have a certain specification. If it's a phone for somebody who is a lot older and is only interested in making phone calls and receiving the odd text, they might want big buttons on their screen because they mightn't have great eyesight, so they might be looking for something that has very big buttons, something that's very simple to use with not a lot of information on it, not a lot of screens around it. So your user requirements would be entirely different for these two types of phones. So that's why it's so important to make sure that it's very clear up front what the requirements actually are in details. The functional requirement specification then would be how is it going to work and what operation of it is going to use it so that the URS can be met. A factory acceptance test, FAT. Factory acceptance test is usually performed at the vendors prior to shipping to a client. The vendor tests the system at the point it's ready to be installed and tested on site. The time spent doing a proper FAT will lead to fewer problems when the equipment is installed on the site. The purpose is to ensure from the outset that equipment is designed to meet certain performance criteria. It should be really unusual to find equipment that won't fit into the building, unless you're working in the Dáil, or equipment that fails specifications in other ways at this stage. However, if it does occur, it's good that it happens at this stage before it's gone any further in the system. Examples of your factory acceptance tests then. So what you might check. So your as-built technical drawings, the electrical, mechanical, pneumatic and process schemes. The maintenance and the user manual, they'd be reviewed. Recommended spare parts list. Certificate of compliance. Materials and equipment certifications. So the steels would need to be made of a certain grade and you'd need certifications for all of those, and your data sheets if you have any chemicals. Instruments and calibration certificates would need to be handed over, and often the verification of the user requirement specification is carried out at the supplier's factory, so it depends on the scale of the project. That would often happen on the supplier side. The SAT, the site acceptance test. So a site acceptance test here, the system is tested to show that it's installed properly and that it interfaces with other systems in the working environment. So it makes sure that it's not been damaged in transportation as well. So the examples of things that you might do in a site acceptance test: finishing the visual checks, so making sure that it's got no dents, no bumps, no scratches, anything like that in it, checking that all the main components are there visually, checking that the utilities and that it is set in properly in where it's going to go, checking that the interlocks are working, so mechanical and both software, checking that safety devices and interlocks are working properly, and delivering some operator training then. So now we're going to do a little case study. So I want you to take a few minutes just to think about what would your approach be to conducting a design qualification for a clean room. If you could pause the slides and have a little think about what your considerations would be, who would you approach to be on the team, and what are the things you would be implementing. DQ of your clean room, so design qualification. So your objectives are what needs to be done and what do the end users need, and that's your job to find out. So the summary of the design requirements. So you need a drawing of the clean room and the HVAC, so the air conditioning system. And much of the clean room validation will relate to the HVAC. So the supply and the exhaust will be really important, and not the actual room itself. That might even be a separate validation exercise. The key design requirements are you need to have a GMP grade environment. So it would be really important that you would know what your particular counts would be, your micro counts. So that's critical to quality requirements, and that would be outlaid in the GMPs depending on what your clean room is going to be used for. GMP style finishes, obviously everything had to be stainless steel. You couldn't have any sharp corners or edges where dust might gather. And again, you'd be following the GMPs to make sure that the style finishes were appropriate for a clean room environment. HVAC, air handling and exhaust units would have to be installed and installed correctly. Your temperature and your humidity control would be checked, and airflow patterns. So where's your air flowing, how's your air balanced, and then the pressure differentials between the clean side and the non-clean side, and how many changes per hour you need. And again, that is defined in the GMPs depending on what you're manufacturing in the room. The critical to quality characteristics for this would be your particulate test, your microbial tests, your pressure differentials, because that's keeping your room clean, and where your air is flowing, your airflow patterns. So these are all critical things that would have to be managed as part of the qualifications. Case study 2. So perform a system and component impact assessment on the process described here to establish the commissioning and qualification requirements. Okay, so this is our process number 2. So it's going to be a batch startup. So here you've got, first thing is verification of your clean mixed vessels by your operators during startup. You weigh out your powder, your dry powder, which is pre-weighed, is added to the mixer vessel, and then you add your solvents. You mix the process together and it is unloaded. So your final solution is transferred into stainless steel drums. The finished product testing. So final solution is tested for conformity to standards. So you're checking viscosity, the assay of the drug substance, and the uniformity of content. They're your tests for your finished product. The mixer then goes back into cleaning and it's washed in place, and you're starting over again with your next batch. Just pause the slides here for a moment and have a think about how you would approach the commissioning and the qualification requirements for a process like this. So this is what your P&ID drawing might look like. So your mixer vessel could potentially have two different products in it, product A and product B. You'll see our batch size for one is 100 and our batch size for the second one is 250, so they're different compositions. This one has 5 kg of dry powder blend and it's got 97 plus or minus 0.1 litres of purified water. This one has a higher volume again at 247 plus or minus 0.1 litres of purified water. The speed mixing again is different for the two different processes. So one is 5, one is 2, and our temperatures are actually the same for both. Our mixing duration is 60 for product A, and it's only 10 plus or minus 5.5 for product B. So just to summarize what the key requirements for this vessel would be. It needs to have the capacity to manufacture all products. So as you can see, you've got two different batch sizes here. You need to be able to fit both in. It must be GMP compliant. So by that, it has to be made of the appropriate grade of steel. It has to be easily cleaned and all of the other requirements that come with the GMPs. The powder is going to be added manually via a detachable hopper. Solutions are going to be added automatically by direct connection to in-house water/solvent supply. And there's an automatic mixer cycle, so the program has to control the duration, the temperature, and the mixer speed. There are important parameters. And wash in place, it has wash in place capability, a WIP capability. So our DQ requirements. So number one, the key design requirements. First of all, we need our vessel to be able to hold 100 to 250 litres. We need a temperature controlled heating jacket around it. We need it to have a wash in place capacity. We need a bottom drive mixer shaft for the agitation, and we need a direct connection to a purified water loop and to a wastewater drain as well. We also need it to have an unloading port, and we need the mixer speeds to be capable of doing 2 to 5 RPM at a variable frequency. So the critical quality characteristics of the mixing cycle area are going to be its mixer speed, duration, and the temperature. The commissioning checks that we might do for this type of a project include the utilities check, checking the purified water and the waste loops. We might check the alarms and the interlocks testing. We would walk down through the P&ID drawing to make sure that all the valves and everything are pointing the right way and the pipes are going in the right order. We would look for calibration certificates, and we would look for the verification of the proper operation, including test sequences, the shutdown, and the startup of the piece of equipment. We would look at the alignment of the hot and the cold water as well to make sure that they were going in the right direction. We would look at the cleaning of the vessel and what it needs to be cleaned with, making sure that it doesn't have any edges that are uncleanable. We would look at the electrical power to make sure that that's okay and it's of the right amperage. We would look at lubrication to make sure that that's all okay, and we would look at the safety checks, including emergency stops. We would look at the drainage of the tank, and we would also look at our solvent or our water connections. We would check that all our valves are correctly oriented, and we would check the pipework and the fittings are tightly secured and safe. So this was our process. We started with our batch, our powder weighing, our addition of a solvent, our mixing, our unloading, finished product testing, and then our cleaning, washing in place. I hope you were able to predict some of these checks. Thank you very much for your time, and we'll see you for the next lesson.